Morning to everyone present here. I am Sangeeta Lakshmi, working as Assistant Professor in UP Department, R.M.K College of Engineering and Technology. So today we are going to discuss about the subject RTL design with VHDL or Verilog hardware description language. So in the unit 1 is introduction to simulation and synthesis flow for the Verilog RTL. So these are the syllabus we are going to see in the unit 1, that is integrated circuit design methodologies, and then Verilog HDL, Verilog design description, and then finally we are going to see some important key terminologies used in the Verilog. First of all, we have to know what is RTL. RTL means it is register transfer level. Actually, it is a high level hardware description language. Usually, why we are going for this kind of high level hardware description languages? Actually, if you want to design any complex circuits without knowing the exact structure of gate level, we need some high level HDL languages. So, RTL will provide you the high level HDL language which can be used to design the complex circuit without knowing the actual structure. So the circuits are described as a group of register in this RTL, and also Boolean equations, control logic, everything we are used in the RTL design. So in this RTL will bridges the gap between the high level descriptions such as algorithms or system specifications and low level gate level implementation. So it is a bridge between these two. By working at the RTL level, the designer can quickly create the complex digital circuits because we are dealing only with the registers, not with the actual structure of the your design in terms of gate levels. But in the RTL, the designer is only dealing with the registers, so it is very easy to design very complex digital circuits. And also, we can easily validate their functionality and optimize them for further improvement in terms of performance like power, area, before they are moving into the physical implementation stage, that is layout design. Some of the benefits of using RTL design in digital circuit development includes faster design cycles due to higher level of abstraction, and it is also easier to debugging and verification of functionality of your intended design. And also it is we have the ability to optimize the design for specific goals such as power, performance, as well as area depends on your applications. And also it can be improved reusability of design components, leading to reduced development times and the cost. So these are the some of the key benefits of RTL design. So the first topic in our unit 1 is integrated circuit design methodologies. That is how the design flow if you want to design any IC. See, in the evaluation of VLSI design algorithms and with the shrinking process node. Actually, now it is 7 nanometer also available. Initially, we are used in the micrometer level. Now it is in the nanometer, even it is shrink to the 10 nanometer. So due to this evolution of algorithm as well as the miniaturized process nodes, the designs are becoming more and more complex, and even the SOC based design are feasible in shorter time period if we are using this kind of methodologies. So the demand of the customer to deliver the product in the short span of time is possible only because of using the efficient design flow which can be implemented in both front end as well as in the back end design. And also the design needs to be evolved from specification stage, that is RTL design to the final GDS2, that is final layout level, which will produce as a GDS2 file which is in the binary file format, which is given to the foundry to design your chip. So the use of EDA tools with the suitable features have made it possible to have the bug-free designs with proven functionality. So nowadays we are using the idiot tools, and it is more precise. Um, it can be used to design any kind of complex circuit without any bug, right? So this is the simulation and synthesis flow. Actually, the designers start from the Verilog RTL design. So already I told you RTL means it is a register transfer level. So you are going to design or any complex circuits can be described by means of RTL. It is a high level abstraction, that is we are dealing only with the registers, not with the exact structure. So any complex circuit we can easily design with the RTL design. So after describing your functionality by using any HDL languages, that can be given for the functional verification. Suppose for example, if you are designing 8-bit adder means you have to design, that is you have to verify that 8-bit adders, um, whether it is actually working as an adder or not. So the functionality we have to check it here by using different test fixtures, that is different combinations of test input vectors we have to given at this stage to verify the functionality of our design. Suppose if our designers pass, if the designers pass, then it is move on to the synthesize step. Otherwise, again we have to change the our program. Suppose if it is passed, the synthesis tool will get the inputs like design constraints, RTL coding, as well as the libraries. These three are the inputs to the synthesize. So the synthesize tool will produces the output which is called as gate level netlist. So the input to the synthesize are library, RTL coding, and design constraint. What is meant by this design constraints? The design constraint means area, power as well as speed. So depending upon our application or requirement, so here we have the area, speed as well as the delay, right? So these three requirements we have to concentrate at this stage. The synthesis tool will produce these all the details at this stage. Suppose if this gate level netlist, the output from the synthesizes gate level netlist. Gate level netlist means it is the description of the your circuit in terms of gates and its connection. So the output from the synthesize will have the gate level netlist. So in that gate level netlist, we are going to check whether it met all the design constraints like area, speed as well as the power. Suppose if the constraint is not met, again it will be going to change the, that is synthesize, that is synthesize is the iterative process until we met the design constraint. Still, if you are not achieving the design constraints, finally we have to change the RTL design. Suppose if the constraint is met, it is given to the physical design. The output of the physical design is GDS2. The physical design involves various steps like floor planning, placement, routing. So the final GDS tool, that is given to the foundry, which can be used to make the chip. So after the physical design also we are going to check the post layout simulation with all the design constraints whether it meets or not. Suppose if it is not, again we have to change in the physical design, that is layout. It is physical design, deal with the layouts. So in this simulation and synthesis flow, three important steps are: one is functional verification, second one is synthesize, and third one is physical design. So that's all today class.